Depending on when you took Chem20, it's either recent or not that recent, perhaps, that you did titrations and learned about stoichiometry. So really what we're going to do is take that concept that you've already learned and apply it to redox reactions. So hopefully we are taking two things that you now know, redox reactions and stoichiometry, and just putting them together. So the first thing is honestly just a bit of review to remind you when you're considering stoichiometry and comparing numbers of moles of one thing to another, what are the steps that you would go through to do that? When you do stoichiometry, you want to have a balanced equation. In particular, in our case, we need to have a balanced net ionic equation, which is like our balanced redox reaction. Is what we're going to use to help us calculate the ratio between how many moles I have of a product or a reactant compared to another. Now at the top there, I just repeated a couple of the mole formulas. Since we've used them already this year, hopefully this is not news to you that there are two ways we can calculate moles. But those two will be applicable anytime we're doing a redox stoichiometry question. So we'll do an example, and in the example, we'll just repeat one more time, balancing redox reactions, and then do some stoichiometry. So the first thing that I'd like us to do in this particular question is to consider that you have acidified potassium dichromate and you have aluminum. And I'd like for you to practice one more time identifying what is going to be the oxidizing agent, what is going to be the reducing agent, and I'll tell you that both of these substances, the oxidizing and reducing agent, are in the data booklet, so we're not going to have to make up half reactions. We're going to use ones that come from the data booklet. So I'm just going to pause here for a second. So folks, I'll just walk you through how I came up with this reaction in case you're still wondering. Anytime I have a redox question, and one thing that someone asked me this morning, how do I know it's a redox question? Usually they will give you some terminology, like in this question the word oxidize is there, so you have an idea it's a redox question. In addition, when you go to write your diploma, the questions are in order, okay? So all of the redox questions are together. I have an acidified solution, so that means I have hydrogen ions. I have potassium dichromate, which is an ionic compound. So what that really means is I have potassium ions and Cr2O7 negative ions. I also have aluminum, not aluminum in a compound, but aluminum. So I have solid aluminum. Because I have a solution, I also have water, so I could note that as well. Now I heard a few people whispering about potassium and where potassium was on the table, but notice that I have potassium ions, not solid potassium. For potassium to be my reducing agent, I would have to have solid potassium. K+ ions are like the second worst oxidizing agent that I have on this table, and since that's what I have in the beginning, it can't possibly be my oxidizing agent because I have dichromate and hydrogen ions, and they are way, way higher up. They're close to the top of the table in terms of their reaction. So I chose the dichromate half reaction for my oxidizing agent. Then I chose aluminum as my reducing agent. It's quite low, so it's a pretty good reducing agent. I wrote the dichromate reaction exactly how it appears in the data booklet. So I would have copied it exactly. So that was my oxidizing agent. Oxidizing agents get reduced, so I copied its reaction out of the data booklet. For my reducing agent, because it's getting oxidized, I wrote its reaction backwards. So I wrote aluminum here, and Al3 positive plus 3 electrons that way. So I flipped the reaction. Very frequently, the reaction that you need, or some of the reactions you need, are in your data booklet. They're not going to ask you, or I'm not going to ask you to write your own half reactions every single time you have to do a redox question. So it's a good idea to at least check that they're there. Then, because there were 3 electrons in this reaction, I multiplied everything here by 2 so that I had 6 electrons. and then I just added my two half reactions together. Now, does anyone have questions they want to ask about balancing redox reactions while we're still on that part? Okay. Once you have a balanced reaction, then you can do some stoichiometry. And so the way that you think about stoichiometry should usually involve a few steps. I am looking for the volume of something. Based on those formulas that I have there, probably the way I'm going to calculate the volume in the end is to manipulate this formula. So I am looking to find how many moles of dichromate I had, because I already know its concentration. If I'm looking to find how many moles I have of something, usually if it's a balanced reaction, I can compare it to one of the other substances if it's known. So when I think about stoichiometry, my first step is to calculate the number of moles for some substance that I know enough about that I could figure out how many moles I have. In this particular case, it's aluminum. I know that I have 5 grams of aluminum, and if I have the mass of something, that's all I need to calculate how many moles I have, because the molar mass is available in the data booklet. So my first step is going to be for aluminum to calculate how many moles I have. So I'm going to take the 5 grams and divide it by the molar mass. Now that's going to tell me how many moles I have of aluminum. I think it's a really good idea not only to write down a unit, but also the substance for which you're calculating the number of moles, because you're going to compare two things and you don't want to mix up which thing you already calculated moles for. Now you'll notice that I wrote my answer underneath because when I do a calculation like this, I actually don't stop my calculation halfway through. I calculate all at once, but I'm going to show you my intermediate answers so that you can see what it is. The next step, here I'll use a different color. The next step is to figure out the ratio. That's what you need the balanced reaction for. The coefficients in a balanced reaction tell you how many moles of each substance or each species you're supposed to have. In the ratio, you should put the number of the moles of the substance that you are looking to find out something about, in this case dichromate, on the top. And the number of moles for the substance that you just figured something out for, my known substance, on the bottom. So in my ratio, I'm going to put the number of moles of dichromate on the top. And I'm going to put the number of moles of aluminum on the bottom. Now I was getting those numbers from my balanced reaction. That's how many moles I need to have of one compared to the other. So I'm going to take my answer to the first step and multiply it by that mole ratio. The reason I multiply it by the ratio in this way is because I'm trying to get rid of moles of aluminum as a unit and figure out moles of dichromate. You'll notice, even though the substance was potassium dichromate, I'm interested in the dichromate part, not the potassium part. The potassium is just a spectator ion. Now when I do that step again, this is just an intermediate answer, but I get 0.0926 moles. The last step in stoichiometry is now to take that number of moles and probably calculate something with it. The thing I'm trying to calculate isn't always the same. So the third step is now to do something to get your answer. In this particular case, I'm looking for the volume of a substance. Sometimes you might be looking for the mass of a substance or the concentration of a substance. So in that third step, you're not always calculating the same value. So here, I know that volume is number of moles divided by concentration. So I'm going to take this number of moles that I figured out and divide it by the concentration that was in the question. Now, because stoichiometry is multi-step, it's really important that you don't round your answer every time you do a calculation. That's why I always show it as sort of one big long calculation to give you the idea that you're not pausing in between. None of those are your final answer. So once I take the number of moles that I got from step 2 and divide it by the concentration, I end up with my overall answer. And here, oops, let's try that again. And here's where I would actually round things off. Now I know my answer is in liters because I was dividing by moles per liter. So that's where I got my unit for volume from. Unless it tells you otherwise, liter is the standard unit that we would use for volume. So this is stoichiometry, a bit of a review. You figure out how many moles you have of something, you use the mole ratio to compare it to something else, and then you use that to calculate your answer. Does anybody want to ask anything about this example? Okay. So then the next step is to take stoichiometry and apply it to some different scenarios that would involve redox. So there are a couple of ions that are really commonly used as oxidizing agents, specifically when we're doing a titration. Titration, you all hopefully would have done one in Chem30E at some point. You have something in the big long burette and you let it drop into a container underneath. And we'll review what all of the words and vocab that goes with that are. But two ions that you should be aware of are permanganate and dichromate. The reason that we use them so frequently is first, they're both strong. If you look in your data booklet, the permanganate reaction at the MnO4 negative is the third one from the top. So there are realistically no substances that won't react spontaneously with it except for that PbSO4 and F negative. The other reason is that they both go through an obvious color change. And because of that obvious color change, it can tell you when your titration is finished. And so we're going to use that, that idea. Now, if I were to look in my data booklet at page 11, where it shows the colors of common aqueous ions, we looked there before when we were looking for evidence of chemical change. I will find some of these ions there. For example, permanganate is deep purple. Dichromate tells you is orange or pale orange, depending on concentration. So you don't have to memorize those colors, but I would say permanganate gets used so frequently that you probably will just know. And permanganate is the one that we are going to use in our redox titration tomorrow. Now, because of this, we could talk about what a titration would look like. So if we did a titration of sodium oxalate with potassium permanganate, and that's the way the sentence was written, where the word of is and where the word with is in the sentence will tell you which substance is which. So if I am titrating something with something else, the thing I'm titrating with, that is the thing that is the titrant. The thing that I am titrating, or sometimes the word of is there so that you can see that, that is the thing that is called more commonly the sample, but very technically the aliquot. Now, it is pretty common for there to be at least a question or two on a diploma where we ask you like what kind of tools you would use. And so when we're considering a titration, this sodium oxalate, because it's the sample, would be in an Erlenmeyer flask, and the potassium permanganate, because it's the titrant, would be in one of those long, skinny tubes that has a little lever on it that's called a burette. Now, because you were expected to perform titrations, we would expect that you know how to do them and that you could identify what tools you would want to use or which substance was where. And so I've seen questions before where they show you a picture of the setup for a titration. They put like a number 1 on the burette, number 2 on the Erlenmeyer, and ask you which substance is in which container. Now, if this was our titration, here's what we would expect to have happen. We would expect those permanganate ions to get reduced to manganese. That means that the color of the permanganate ions, which is purple, should, because there's sodium oxalate in the sample, be changed right away to this colorless color for the manganese ions. If, though, I've used up all of my sample, so the amount that I have in my Erlenmeyer flask, all of it has reacted, and I keep adding permanganate, the next time I add a drop of permanganate, the solution will start to look pinkish purple. It usually looks pink right away because the concentration is lower, and it would look purple if you added a higher concentration. So the reason this is so useful is because that's how you know the reaction has ended. That's how you know how much it took of each substance to cause a reaction and for the reaction to go to completion. Yep. So the other thing that's here before we get to the example is the list of steps that you would need to complete a redox titration. So a lot of this stuff we will actually practice in our lab tomorrow. The first thing you need is a standard solution. That means you need something with a known concentration. If you don't have that, you can't do a titration. It doesn't matter which substance is the standard. It could be the titrant or it could be the sample. Frequently, it's the sample, but it doesn't have to be. So at least one of the two substances has to have a known concentration. Then you measure out a known volume using a pipette. Do you remember what a pipette is? It's a long, skinny thing, has a little ball on the top of it. You suck the liquid up with it. We're going to use them in the lab. That's another tool that would go along with this. And I've seen them ask questions like, how are you supposed to measure things when you're doing a titration? And this would be what you would choose. The burette is the long, skinny tube that has a little valve at the bottom. You fill that with the titrant. And then you titrate the alcohol or the sample with the titrant until you get to the end point. Now, all of that is all sort of technical. What do you do? Which container do you use? What tool do you use? Number 5 is a little bit more about data. You need 3 concordant pieces of data. That means you have to do several trials, at least 3, often more like 4, so that when you get to the end of your titration and you look at how many milliliters of titrant you had to add, 3 of your trials are concordant, meaning they are within 0.2 milliliters, which seems really small, but your burette is measuring tenths of a milliliter, and so you can get really, really specific data there. So we will do an example of the calculations that go with the titration. Very frequently in a titration, what you are looking for is the concentration of one of the two substances. Most of the information that you need is actually in the title of the table. And so don't forget that that information is there. In this particular question, we're looking for the concentration of those permanganate ions. And in the title of the table, it tells me a volume and a concentration for one of the substances. When I look at this table and I read what's happening, I'm titrating C2O4 2 negative with MnO4. Because that word with is there, I know that MnO4 is the titrant, and so I will get its volume by looking at the data from my titration. Now, when you're looking at the different trials for a titration, what you should do is take the difference between the two readings. Regardless of whether you think the answer is negative or not, don't. You're just looking for how many milliliters you used. So when I take the difference of each of these, I get 15.6, 14.65, 14.55, and 14.6. So all I'm doing is finding the difference between the final and the initial reading on the burette, so I know how many milliliters of my titrant I added. Now in that list of instructions, it said that you needed 3 trials that were concordant, meaning they were within 0.2 milliliters. That means when I look at this data, I am not going to use trial 1's data, but I will use the data from the other 3 trials. So frequently what they'll do in a titration question is give you more trials than you need so that you know which one of them you would knock out or which one of them you wouldn't use. For the ones that you would use, those 3 trials, you take the average, and so the average of those 3 trials is 14.6 milliliters, and you're going to use that as the volume of titrant that you added. So I didn't use that 15.6. And when you guys do your titration, what you'll see is that often on the first trial, you really have no idea how much titrant you're going to add. And so people will sometimes overshoot the endpoint on the first trial. And then for the second trial, because you have an idea when the color is going to change, you go really slowly when you get close to that volume. That way you can get a more precise measurement. Some of you might do a really fantastic job and have 3 good trials right away when you do the titration, and that's fine too. The idea though is that you need 3 that are concordant and you take their average. Now, if we're doing any sort of calculation with a titration, we also have to know the reaction that was happening, and it needs to be balanced. This is an example where I might use oxidation numbers instead of half reactions to balance this, and here's why. I'm not actually interested in what the coefficient for hydrogen or water is, because I'm not going to use it in the question. I care about this coefficient and this one. So I might consider oxidation numbers here as a quicker way to get to that. When I think about that, I would compare my carbons here, and I would see that it went from +3 to +4. So it lost an electron. Then because there are 2 carbons here, I would put a 2. For the manganese, it went from +7 to +2. So it gained 5 electrons. Then my next step would be to make sure I'm gaining and losing the same number of electrons. So I would multiply this reaction by 2 and this reaction by 5. There's all the coefficients that I need. I could keep going and balance the whole thing and make sure I have enough hydrogen and water, but what I really needed was the coefficient for my 2 reactants so that I could do a calculation with it. So this is a good example where, if it were me, this is how I would do it because I got to my answer faster. Now, if I was going to balance the whole thing, I would also add an 8 here to balance oxygen, and then I would end up adding a 16 here to balance hydrogen, and always in that order. Balance oxygen first with water, balance hydrogen second using hydrogen ions. Does anyone want to ask questions about balancing or about figuring out average volumes in a titration? So we're going to follow the same 3 steps that we followed in the first example. First step, get this out of our way. First step is to calculate the number of moles for my known substance. So essentially, which of the two things do I already know how many moles I have of? Well, I know the volume and the concentration of C2O4 negative, so I could figure out how many moles. So I'm going to multiply the concentration with the volume, keeping track of which units I'm using. Since I'm using moles per liter in my concentration, it's a good idea to use liters for your volume too, so that you don't accidentally have an answer that is 1,000 times off what the answer actually is. So 10 milliliters is 0.01 liter. Now my intermediate answer, which is not my final answer, so I wouldn't round it, is 2.27 times 10 to the power of negative 4 moles. Because I'm figuring out the moles of C2O4 negative, I'm just going to jot that down so that I know which thing I was calculating with. In the end, we're going to find the concentration of permanganate. Yeah. Second step is to use the ratio between this substance that I know something about and the one where I'm trying to calculate something. I'm looking for the concentration of permanganate, so I'm going to take the ratio between oxalate and permanganate ions. So I'm going to take my C2O4 negative. Now, since that's the one whose number of moles I already calculated, it goes on the bottom. Since permanganate is the one I'm looking for, it goes on the top. Now I'm just going to take my answer from the first step and multiply it by this ratio. So if it were me, I wouldn't even clear my calculator. I would keep my answer from the first step, multiply it by the ratio. Oh, I guess I should write this down. So the intermediate answer that you get there, if you're keeping track of them, is 9.08 times 10 to the power of negative 5 moles of MnO4. Now I'm just going to take the answer from this step and use it to figure out my concentration. I know that concentration is moles divided by volume. So I'm going to take my answer from step 2, that's the number of moles, my average volume. Now remember, you want to make sure your units are in line. So since I've been using moles per liter and liters, it might be a good idea here to use liters. So rather than 14.6 milliliters, I switched it to liters. Yes? So you multiply by the top number and divide by the bottom one. So if I'm typing this into my calculator, I would go times 2 divided by 5. Sure. Does anyone else have questions about any of the steps here so far? Okay, so if we've done all of this, the answer that we get for concentration should be 6.22 times 10 to the power of negative 3 moles per liter. Moles per liter is the concentration unit that we use the most frequently. If that was your answer and we were looking for a numeric response, you can't write that the way it is into a numeric response. And so in some of the practice diploma questions, you'll see this, but we'll call each of the letters or each of the numbers a letter. For example, the 6 would be A, the first 2 would be B, the second 2 would be C, and the negative 3 would be D. And they would ask you, what are A, B, C, and D? What are those numbers? So if your answer actually is in scientific notation, that would be the way that we might ask you to fill it out. And so in a numeric response, if this is how they were asking it or I was asking it, you might fill in 6223 as your answer. If you got an answer that was small like that, and there was no indication that your answer should be in scientific notation, then you did something wrong in the calculation. So there would never be a question where you can't actually fill your answer in to a numeric response box.